For decades, the moon has been a distant memory, a silent witness to humanity's first great leap. Now, NASA's Artemis program is turning that memory into a living mission. The plan is bold: to build a permanent base camp at the lunar South Pole, a place where sunlight grazes the peaks while craters below remain frozen in eternal night. Astronauts will live and work there for up to 2 months, testing the systems that one day could carry us beyond the moon, toward Mars, and beyond. This time, it's not just NASA. It's a global alliance: ESA, JAXA, Canada, and private companies, all shaping the blueprint for humanity's first off-world city. We once visited the moon. This time, we plan to live there. But before the first human ever sleeps under that alien sky, the moon will test everything we know about survival. Beneath the promise of sunrise on distant peaks lies a more dangerous truth. The moon's dust is not harmless powder. Regolith grains are razor sharp, fractured like shattered glass. And under the stream of solar plasma, they carry electrical charge. In the low gravity and vacuum, these electrified shards cling to suits, abrade seals, and jam mechanisms, a silent, invisible enemy that works slowly and relentlessly. History taught us how small the threat can become. When Apollo 12 visited Surveyor 3, the probe lay 180 meters away, yet the lander's exhaust had sandblasted its surface. Equipment meant to sit quietly for years bore the scars of a single mission's dust plume. If a single landing can scour metal hundreds of meters away, imagine the effect of constant departures and arrivals around a permanent base. Modern studies add another. Stranger layer-charged dust can generate small discharges across surfaces, producing microsparks that interfere with electronics and pose risks to sensitive sensors. NASA's recent testing with regolith simulants shows that electrostatic effects are real. They produce clinginess and can create tiny arcs on suits and instruments. This is not just an annoyance, it is a systemic threat to long-term operations. We must treat dust like the central design constraint. It is every landing plume, every rover wheel, every footstep becomes a potential erosive event. Solutions will have to be holistic, hard surfaces and roadways to limit mobilized dust, electrostatic mitigation systems to repel charged grains, and maintenance strategies that assume abrasion as a constant. It clings, it cuts, it kills machines. To survive it, we may have to melt the moon itself. The solution to the moon's deadliest problem begins with light. In the laboratories of Earth, engineers have learned to weaponize heat-transforming powder into pavement. At the European Space Agency, a high-powered laser slices through trays of lunar soil simulant. Each pulse fuses the grains together, melting them into smooth, glass-like tiles. The process is slow: 115 days for a single 100 square meter pad, but the result is breathtaking. A hardened surface, ready for landers, rovers, and human footprints that won't sink into dust. Across the ocean, NASA's SwampWorks team has been experimenting with microwave sintering, where radio waves heat the dust from within. The method is 10 times faster and far more efficient, melting entire layers in minutes instead of hours. In tests at Kennedy Space Center, the solidified regolith reached a compressive strength of 206 megapascals, stronger than Portland concrete on Earth. What begins as grey dust becomes luminous stone, not through brute force, but through precision. Every beam, every spark, reshapes a world that was once unbuildable. We can turn dust into stone, one beam of light at a time. But some engineers say, let the sun do the work. On the moon, Sunlight is more than illumination. It is raw energy waiting to be shaped. If lasers and microwaves are our hammers, then the sun itself is the forge. Engineers are now experimenting with Fresnel lenses, thin, grooved discs capable of concentrating sunlight into a focused beam hotter than 200 degrees Celsius. A single 2.5 meter lens could melt lunar dust into glass tiles, layer by layer, using nothing but light. But there's a challenge. At the lunar South Pole, where Artemis plans to build its base, the sun never climbs high, hovering only 5 to 10 degrees above the horizon. The light is long, low, and cold. To catch it, NASA plans to deploy heliostat mirrors, robotic panels that track and reflect sunlight into the Fresnel arrays. Together, the lenses and mirrors could form a network of mobile furnaces, factories of light crawling across the moon's surface, melting and paving as they go. In time, this could lay the foundation for runways, habitats, and the first real lunar roads. Every beam of sunlight becomes a builder's torch. And once roads exist, the moon becomes a map. In the silence of the lunar South Pole, motion itself feels like defiance. Every wheel that turns, every plume of dust that rises, is a declaration that life can move even here. The Lunar Cruiser, built by JAXA and Toyota, is not just a rover, it's a pressurized home on wheels, designed for 2 astronauts, powered by hydrogen fuel cells. It can sustain life for 30 days without outside support. Inside, the air is breathable, the temperature stable, the silence constant. Outside, there is only the void. NASA's upcoming lunar terrain vehicle will take on the heavy work, carrying up to 800 kilograms, climbing slopes as steep as 20 degrees, and exploring up to 20 kilometers from base. These machines will become the arteries of the lunar city, hauling tools, samples, and hope across a world without roads, in low gravity. Every bump can launch a ton of dust. That's why precision driving, sealed joints, and static shielding aren't luxuries, they're survival tools. Each journey is a choreography between caution and courage. Through the thin light at the rim of the South Pole, a convoy of rovers crawls toward the horizon, their shadows stretching for miles across the dust. But explorers can't wander forever. They need a home that breathes. Inside the pale silence of the moon, a new kind of home is taking shape, not built to last forever, but long enough to prove that humanity can. NASA's Foundation Habitat is the first true lunar house, a 3-story structure designed to support 4 astronauts for up to 60 days. According to the 2024 internal layout of a lunar surface habitat study, the crew will need at least 92 square meters of sealed space just to live, work, and stay sane under lunar isolation. The first floor is the airlock and geology lab, where astronauts strip off dust-caked suits and examine lunar rock samples under pressurized conditions. Every speck of regolith here is treated like gold-studied, sealed, and logged before it ever leaves containment. The second floor expands into an inflatable module, housing a biology lab for plant and microbe studies, alongside an exercise zone to prevent muscle loss in low gravity. Treadmills and resistance bands float under soft light echoes of earthly habits preserved beneath alien skies. On the top floor lies the living deck bunks, medical bay, and a compact galley for shared meals. From the small circular window, Earth hangs like a fragile blue marble against black infinity. Yet beauty comes with danger. Radiation levels on the moon average 1.3 millisieverts per day, about 30 times higher than Earth's surface. To survive, the habitat must be buried under 1 meter of regolith or shielded with a Whipple multi-layer roof capable of deflecting micrometeoroid impacts. The foundation may be small, but it's humanity's first breath beyond Earth, fragile, deliberate, and alive. But this home won't last long unless we turn the moon into our armor. To turn the moon into our armor, we must learn to build with what it gives us: dust, not imported steel or concrete, but the ancient powder under our feet, regolith, the raw material of survival. In 2024, NASA's NIAC RAMS project tested a new kind of sintered brick made entirely from lunar dust fused by heat and pressure. The result was astonishing silicon-rich bricks that can withstand temperatures from 196 degrees Celsius to plus 1,450 degrees Celsius and carry loads of over 2 tons. But these aren't just walls, they're factories. Through electrolysis of molten regolith, scientists can separate oxygen for breathing and metal alloys for construction. The byproduct of survival becomes the foundation of architecture. Meanwhile, engineers are spinning basalt fibers from regolith, ultralight threads stronger than steel. Perfect for insulation and flexible structural panels, each filament is born from dust, yet holds the strength to shelter life. Every grain of dust becomes a future wall, and some nations are already firing their first lunar bricks. The dream of building on the moon is no longer owned by one flag. It has become a global construction site, a new kind of race, not for conquest, but for endurance. China has taken an early lead with its moonpot vessel concept, a 3D printed ceramic habitat built entirely by robots. The design merges ancient architecture with modern automation, using lunar soil as clay. Since 2024, prototypes have been undergoing 3-year exposure tests outside the Tiangong space station, enduring radiation, vacuum, and thermal swings that mimic the lunar surface. In Europe, ESA and Thales Alenia are developing the multi-purpose Habitat MPH, a modular living system designed to last over a decade. It can function autonomously in uncrewed mode, running life support and thermal systems remotely between missions. ESA calls it a smart home for the moon, one that can rest, repère, and wake up again when new crews arrive. Meanwhile, in the United States, Skyports is pushing the limits of imagination, proposing to literally blow glass domes in vacuum. By heating lunar dust into molten glass and inflating it with compressed gas, they could create vast, transparent structures, layer by layer, like bubbles frozen in time. The race is not to arrive, but to endure. Yet even endurance needs one thing: no nation can ignore water. At the edge of eternal light lies a place where the sun has never risen, a realm of shadow and ice. The permanently shadowed regions, or PSRs, inside Shackleton Crater, sit at a staggering 230 degrees Celsius, a darkness untouched for billions of years. These craters are not dead, they are treasure vaults. Radar and neutron data from NASA's Artemis program suggest that billions of tons of frozen water lie just 0 to 1 meter beneath the surface, preserved in the same dust that threatens to destroy our machines. To reach it, NASA is developing heated drills and thermal tents, robotic systems that can bore into the frozen ground while trapping vapor before it escapes into space. Every droplet must be captured. Every gram matters. Once extracted, this ancient ice will be split through electrolysis, separating hydrogen and oxygen to create both fuel and breathable air. Water becomes the key to movement, to survival, to staying inside these shadows. The moon holds its most valuable secret, the element of life itself, But in a place that cold, even sunlight can't save you, the moon does not spin like Earth. One full day here lasts nearly a month. 14 days of sunlight, followed by 14 days of darkness, and in that long night, temperatures plummet to 170 degrees Celsius, freezing metal, draining batteries, and silencing machines. The difference between lunar day and night exceeds 250 degrees Celsius, a thermal swing violent enough to crack glass, warp seals, and destroy unshielded electronics. Even the most advanced solar-powered rovers have died during these cycles, their systems frozen solid, waiting for a dawn that never came. To survive the darkness, NASA plans to harvest the light that never dies, building solar towers on the peaks of eternal light. The few ridges at the lunar South Pole that remain sunlit year-round. From there, direct current cables could transmit energy down into the shadowed craters below. Another idea, microwave beaming could transmit power wirelessly, turning radio waves into light for the cities below. The moon may be silent, but its skies could one day hum with invisible energy. When light fades, only the prepared endure. That's why NASA plans to build a small sun of its own. Beneath the silent dome of lunar night will beat a very small, very steady heart. A power plant, no bigger than a car and colder in temperament than any furnace on Earth. NASA's Fission Surface Power Program aims for reactors under 6 metric tons, capable of producing 50 to 100 kilowatts of continuous electricity, enough to run habitats, life support, factories, and the heaters that keep pipes from freezing in 2 weeks of darkness. These are not skyscraper reactors, they are compact, hardened machines designed for space, shock tested, shielded, and built to run with minimal maintenance. Companies with decades of naval nuclear experience, Rolls-Royce among them, are adapting submarine microreactor technology into designs that can be stacked multiple units, linked into a resilient microgrid that grows with the settlement. Stack 3, and you power a small industrial complex, Stack 10, and you begin to speak in megawatts. There are practical advantages to putting them where the sun never shines. A reactor lowered into a permanently shadowed trench enjoys a naturally cold sink, simplifying heat rejection and stabilizing output. It can be buried and surrounded by regolith for additional passive shielding, reducing both thermal stress and stray radiation. In short, the dark is not merely an obstacle, it becomes a partner for safe, steady power. Of course, this raises questions of launch safety, emplacement, and redundancy, how to land a reactor intact, how to isolate it during assembly, and how to design fail-safe cooling in a vacuum. The engineering answers are bureaucratic and boring redundant controls, remote emplacement robots, and containment barriers, but they are solvable, and they are being tested in concept today. Imagine a cluster of silent boxes buried around a habitat. Their faint thermal glow, measured only by remote instruments. They make no sound the way a diesel makes sound. But their hum is the most important heartbeat of the settlement, a silent core beating beneath eternal night. And with power mastered, the moon stops being a destination and becomes a beginning. The moon was never meant to be an endpoint, it is a bridge. By the time Artemis 4 carries the first elements of the gateway into lunar orbit, we will have more than a return mission. We will have a staging ground, a hub to move crew, fuel, and parts between Earth and the wider solar system. The gateway will act as a traffic circle in space, a place where modules rendezvous, cargo is repacked, and crews transfer from deep space transit into landers bound for the South Pole below. Linked to surface systems, the multi-purpose habitat The regolith factories. The power. Microgrids, this orbital outpost turns the moon into logistics. Not just a postcard. What we learn here about living off Earth, spinning basalt into beams, mining ice and splitting it into fuel, running a silent reactor beneath a trench of shadow becomes the template for missions to Mars, to near-Earth asteroids, and beyond. When we learn to live off Earth, we free ourselves from it not to escape, but to expand. Imagine the final shot. The lunar base glows faintly in the long dusk. Its lights mirrored back as a pale thread across the face of Earth. Then pull back further until that thread points toward a rust-red dot Mars. Between the lab bench and the silence of the crater floor, between the flashlight and the star, a single truth remains: we build not because the moon is easy, but because it teaches us how to stay. Between science and silence, this is how humanity learns to stay. Next time, we will go deeper into the shadows, where frozen water waits to be freed and turned into life.